Hello everyone, this is Jiming Sun. Today I'm going to talk about a paper from our lab that recently published at the Cell Patterns, SECONDGRAM, self-conditioned diffusion with gradient manipulation for longitudinal MRI imputation. And it's led by my students Brandon Theodora and in collaboration with our collaborators from NIH, Anand Dadu, Mike Knowles, and Faraz Fagari. So the high-level summary of this work is we introduce a new method for longitudinal MRI imputation. It can track the brain changes over time, addressing the issue of scarcity of the paired MRI dataset. Through these techniques, I will talk about self-conditioned diffusion and the gradient manipulation techniques. Why does this matter? In a lot of neurodegenerative diseases, such as Alzheimer, Parkinson diagnoses, it really requires a good understanding of progression. So you need not only a single MRI, but really you want a longitudinal MRI. But such data is actually very limiting, and this paper addressed this data scarcity challenge, introduce a data augmentation strategy to handle that type of scenario. The challenge of longitudinal MRI data. It's a very scarce data set. We usually have very limited paired MRI data. That meaning that you have this initial MRI scan, and maybe a couple of years later you have a follow-up scan. So that will be an ideal data set. But those longitudinal data sets are often very rare. For example, in this UK Biobank data, we only have about 5,000 patients have those longitudinal data, have a follow-up, and vast majority, tens of thousands of patients have only single scans. Another challenge is data disparity, where you have this very small portion of patient data have a follow-ups, but vast majority have a single scan. How can you use both data sets in your research or in your modeling? And the clinical importance, as I said, right, both Alzheimer and Parkinson diagnoses require understanding of disease progression. To handle this lack of longitudinal nature of most of the data is a very important challenge. So what's our approach? The core idea is this two technical contribution. One is called self-conditioned learning, and where we leverage those unpaired MRI data and condition those images on a possibly a noisy version of themselves, then transform a single time point of data into a paired data. Once we have that simulated or augmented paired data, then we can combine them with the actual real paired data, have a much larger data set, then continue the model training process. Of course, you encounter some of the challenges to handle such combined data set, which I will introduce later, and this gradient manipulation approach become very important. So you can introduce to enable more robust training when you have low data settings. So here's some of the steps. Step one, we convert the raw MRI scan into 769 anatomic features, such as volume, thickness, areas, and so on. Then we use those high-dimensional feature vectors as our data set, then continue the remaining steps. we combine the data set of 5,000 paired MRI, the real longitudinal data, with 37,000 unpaired MRI, and this unpaired ones will be augmented through self-conditioning. So we have created this combined set of all those paired data. Step 3 will be extracting those features and then train a diffusion model with gradient manipulation techniques for stability. And then finally, we'll generate realistic follow-up features for initial MRI and also plus their patient demographic information. So, result, we'll be able to have a 5 times more training data and 20% better prediction accuracy, as I will show you later. Now let's look at some of the concrete technical ideas. The key ideas is self-conditioning, conditioned learning. The problem is you have this pair data. That is what you want, but that's rarely available. So, for example, only 5,000 patients out of 41,700 UK Bioband dataset have both the initial and follow-up scans. So those paired dataset are the true longitudinal pairs. You have MRI at time point 0 and then MRI at maybe 2 years later. And this is what we actually want to learn from. We want to know, does the brain change over time? But we also have a large or abandoned data set of these single scans without follow-ups. We have about 37,000 of those patients, only a single scan in the UK Bioband data. And we don't know what happened to this brain later. And traditional approach will be just ignoring those data set altogether, which is kind of wasteful. And a clever solution we propose, or actually a quite simple one, is what if we turn this abandoned single scan into some synthetic training pairs? How do we do that? If you have the pair data and you just condition the second visit, condition on the first visit, and the label, which data, and if you have a missing the single scan, what we'll do is we'll condition on the image itself or a noisy version of that image. Very simple idea. So the key insight is this augmentation will teach the model the basic MRI patterns, what make a valid MRI, because you have tens of thousands of those MRI. And will help us understand the feature relations, how they correlate, and how the age, gender affect the brain structure, and so on. Here's some visualization of example of those, the real data versus the generated data for the second visit. You can see once we learn such a model, you can actually simulate the second visit from just the real first visit. That's pretty cool, but this actually introduces instability when we construct the training data this way. So I'll talk about this gradient manipulation approach. The challenge here is when you have only a small percentage of the real pair data, this 5,000 pair data, and the model can easily overfit this smaller data set. The model might remember specific patient rather than the general patterns. When we introduce this self-conditioned synthetic pair of data, actually introduce some heterogeneity into the data set. But the model has to learn 2 different tasks, right? Task 1 is from the first MRI to the actual second MRI, this true progression task. Task 2 is really an identity mapping, right, from MRI to MRI 1 itself. So these two tasks are very different, require very different loss landscape, and the grading in those different tasks can conflict to each other. And it also risks the gradient updates to be extremely large, in this case, and unstable if you incorporate just naively use those updates. And because a single bad update can unlearn everything the model has learned so far. And this is very dangerous in this mixing training objectives. So what we did here is actually a quite straightforward approach, and we first compute the L2 gradients norm when we first after each batch of data. So that magnitude will give us kind of a notion of how big the gradient update will be, right? Then we run a preliminary pass over the data set to figure out the two thresholds. One is a clipping threshold, one is skipping threshold. So clipping threshold is lower and skipping threshold is higher. I think it's 3 times higher. And what it does is if it's below the clipping threshold, you just apply the gradient update as it is. If it's above the clipping threshold but below the skipping threshold, we will do some kind of a scaling so that we regularize that large update. But if it's above even the skipping threshold, we're going to skip that particular update because the gradient is too large. Okay, so that's gradient manipulation. With this strategy, our methods can successfully combine the self-conditioning with real longitudinal data and achieve a much better result, as I will show you next. So next I will talk about experiment setup. So we use the UK Biobank data where we have a 41,000 total number of patients, 5,000 with the paired data. And among those 5,000, the average year time gap between the initial and the follow-up visits are 2.67 years. The architecture, we use a UNet-based diffusion model and the residual blocks for feature refinement and 100 diffusion steps. In evaluation metrics, we'll talk about similarity metric to assess the quality of individual MRI feature vectors, and we also will look at the distribution of the entire data set and see how they're similar to real data, and then also evaluate some downstream application and case study. So let's look at the first task, which is we want to understand how well does the model predict specific patients' real follow-up MRI. Right here, we use the patients who actually have both initial visit MRI 1 and the follow-up visit MRI 2. And so given the model, the MRI 1 and the patient information, our model will predict MRI 2. Then we compare MRI 2 with the real MRI 2. So the metric we're using are Pearson correlation. The larger the better. Euclidean distance, the smaller the better, and the cosine similarity also smaller the better. And we'll compare a whole bunch of different methods. SECONDGRAM outperform the best baseline by 20% in Pearson correlation, for example. And we also did an ablation study, compare the degenerative version of SECONDGRAM without the self-conditioning or gradient. See that both technical components are quite essential, or if you don't have them, the performance actually degrade quite a bit. So that's for individual image features. Next, we're going to see the distribution level. How well does the synthetic data set as a whole look like the real data? And here we're testing some statistic properties such as Frisch's distance and Pearson correlation, mean correlation. And here is the lower the better. SECONDGRAM actually significantly outperform all those baselines. And again, those ablation study, those two techniques, self-conditioning and gradient manipulation, are actually important. We have a 27% improvement over the next best baseline. And here are some visualization of the result. For example, you look at the real data, the PRS correlations here versus SECONDGRAM. You can see there are some visual similarity, while all the other baseline visually look quite different. So that's the distribution evaluation for the entire data set. Next up, we're going to see how we can use those augmented data for some downstream applications. And in particular, we're looking at two classification tasks. One is for Parkinsonism detection. Can we identify patient with Parkinson's disease earlier? And then we look at the stroke classification, and can we detect patient who had a stroke? So here you can see that for when you compare all this different method, and the SECONDGRAM is the one in the bottom, you can see there's a significant improvement, up to 10% improvement in the stroke classification. And for Parkinson detection, the performance gain is also present, but much smaller. So that's the downstream application. And we also did a case study for Parkinsonism. And here, this is a real-world validation of, instead of just measuring some statistical performance, we want to test the SECONDGRAM capture the actual medical knowledge about disease progression. So here's some medical background, which is very interesting. And there's a region in the brain called the substantia nigra pars compacta, or SNC. And that's the location of this SNC region is a small region deep in the brain stem. And the role of this particular region is it contains dopamine producing neurons. And the role for this region is this is where Parkinson's disease actually starts, and there's no medical fact that Parkinson patients, for Parkinson patient, this SNC volumes decreases faster than normal aging population. And there's early sign of SNC degeneration often precede the symptom of motor functions. And so this could be a very interesting early diagnostic markers from MRI to detect this SNC atrophy. So we extract patient in this particular setting. We have this follow-up data. We found patient with both initial and follow-up scans and separate this into two groups of cohorts, right? One is have this condition, Parkinsonism. We have a very small portion of them, 107 of them. We see there's the kind of significant degradation, reduction of this region, SNC volume, and then everyone else, right? So for those patients, we measure with this condition, we measure the volume change is minus 2.36 millimeter cube, and then without this condition is minus 1.76, right? You can see about 34% reduction in volume. And if we use the SECONDGRAM to measure the changes, you can see the change for the group with the condition is minus 454 to minus 3.49. It's again also close to 30% of reduction. It's kind of a validation of SECONDGRAM actually capture the correct trend and also the progression of the progression, right? So it's more decay that happened for this population. Okay, So we're almost done with the implication and impact of this work. We have some interesting impact on medical imaging analysis, right? So now we can maximize the use of available MRI scans. We don't have to just limit to the ones that have longitudinal visits. We can actually use all the data set, even for single scans. And because of this data benefits, we can actually accelerate, enable some research study that really require this paired data. And we hopefully can enhance some longitudinal disease monitoring in some clinical applications. So what are some the limitations and future work for this? One, we in this work haven't modeled this variable time gap, right? So we actually, in the real data, for the paired data, we know the duration of these two scans, and that maybe play an important role to model the more granular progression speed. And in this work, we didn't leverage that time gap. The second limitation or future work potential is leveraging multi-modal imaging data. So here we only look at MRI, but we could potentially look at other imaging types such as PET scan, fMRI, DTI, and CT scans, right? So those are also popular imaging modalities available out there, and we can consider combine them. And in this particular work, another limitation is we're generating the important MRI related feature, that's 769 features, and we are not generating the raw images. So a step forward could be taking those features and do a full MRI image generation, right? So that can potentially recover some of the spatial details, and visual validation become possible, and you can also use those high quality image data for advanced analysis that require those imaging data. And ultimately, we also want to conduct this entire experiment in real world clinical settings. That's another potential future work. So in conclusion, what we talked about today here is a novel framework called SECONDGRAM for longitudinal MRI feature imputations, and the technical innovation include this self-conditioning approach to leverage unpaired data, those individual scans, together with paired data, that the real longitudinal pairs of initial and follow-up scans. And we have some gradient manipulation approach to ensure the learning stability, and we have shown that the performance of the model is significant over many other baseline augmentation strategy, and this approach can be used to improve classification performance for the other real disease diagnoses. So if you like the work or have questions, feel free to contact us, and we listed some of the authors' contacts here, and the code and the paper is also available. Please check them out and try them.